In this video, we will be looking at the action potential. Make sure that you have watched the first video on this, the resting potential, before you try and watch this video. With the resting potential, in this picture here, this is inside the axon of the neuron. This is outside the neuron. And inside is minus 70 millivolts. The potential difference between the inside and the outside is minus 70 millivolts. All to do, as we said, with the sodium-potassium pump. And we are pushing 3 sodium out and 2 potassium in per ATP. So net negative inside because you've got 3 positives outside and 2 positives inside. Also helped by the fact that we do have some potassium channels open, which will allow the potassium to diffuse back down its gradient to the outside, taking more positive charge with it, so becoming more negative inside. And also these voltage gated sodium channels, which would also let movement of sodium down its gradient, are closed at minus 70 millivolts. So this would be facilitated diffusion, but it's not occurring in this case, but will occur when we get that action potential. This is also facilitated diffusion, but can occur and helps to make the inside more negative than the outside. And then we remember that this sodium-potassium pump is active transport. There is loads of information on this graph, but this is an action potential, and that's what we're going to be talking about today. An action potential occurs when the neuron is sending an impulse down an axon, and we are going to get a change from minus 70 up to plus 40 millivolts and then back down again. So this is the resting potential, and the reversal up to plus 40 is the action potential. And we've got a number of different stages, and what we'll do is we'll talk about some of these stages now, and other aspects of this we will mention in later videos. The aspects we're going to talk about today, we're going to talk first about depolarization, where we start to become positive. We'll talk about what happens at the very top, the plus 40. We will talk about repolarization, so back down to negative inside. We'll talk about this area of hyperpolarization, where we become too negative, and then we're going to return back to the resting potential. So we'll talk about each of these stages in turn. So we've had resting potential. We're going to go into an action potential, and the first stage is depolarization, and we've got stage 2 shown on here, and stage kind of 3 are all depolarization. And we'll talk about these stages in turn. If we start with the first part of it, there's been a stimulus saying we want to send a message, and this stimulates the opening of voltage gated sodium channels. So voltage gated sodium channels mean that sodium diffuses into the axon, and it's facilitated diffusion, so down its gradient. And what will happen is the inside starts to become less negative, and you can see that on the graph here. We start to become less negative. We then have stage 3. We get this rapid depolarization. The fact that you've become less negative means that other sodium channels open. It's kind of a cascade of sodium channels opening. So more sodium channels open, which means that more sodium floods into the axon, bringing with it the positive charge. So it means that we will get up to the plus 40 of the of the action potential itself. One thing to mention just here, just briefly, and we will come on to this at a later in a later video, you have got a level across here called the threshold level. And the threshold level is between -50 to -55 millivolts. And this, you have to get over this level in order to get an action potential. So even if you get a little bit of sodium in and only get to like -60 millivolts, that won't be enough to get over the threshold level. So this is linked to something called the all or nothing response, and you'll have a later video all about this, but I just want you to be aware of it now. The peak of the action potential is shown at number 4, and what here, it's going to be +40 millivolts. Always +40, it's not going to go more than that. That's the size of the action potential. And what happens here is we are going to switch from depolarization to repolarization. So the voltage gated sodium channels will close, and the voltage gated potassium channels will open, and this will allow potassium to flood out of the axon through these voltage gated potassium channels to bring about repolarization. Repolarization is shown at stage 5. So in stage 5 we had those voltage gated potassium channels open, so the potassium floods out of the axon through the voltage gated potassium channels and take with it its positive charge, so we become negative inside the axon. So that will shoot us down into negative again. What will happen though is shown in stage 6. So stage 6 is showing you hyperpolarization. So lots of potassium diffuses out of the axon, and we actually overshoot the resting potential. So we want to be -70, we become more negative than -70. But what will happen is the voltage gated potassium channels will close. We're going to restart the sodium potassium pump, and this will work hard to re-establish the resting potential, moving the sodium out and the potassium in to get back to -70 millivolts. And you can see it takes a little bit of time to get to back to the resting potential. Now this hyperpolarization stage is a really important stage. It's where we have something called the refractory period. And again, we're going to talk about this more in a later video. In this video, we've spoken about what the action potential actually is using this graph, how we've got the depolarization caused by the sodium ions flooding in to the axon, repolarization caused by potassium flooding out of the axon. But we've not talked about how this action potential actually moves along the axon of a neuron. So this propagation of an action potential will be talked about in the next video. Thank you.